there is your equation for half-life. So let's go back where we left off here. We'll talk about this, and this is me explaining all that stuff right here. So let's take a look at this example. What is the half-life of a substance in a first-order reaction that has a K value of 0.0125 seconds to the -1? So, you have a half-life, you have a value of K, rather, is 0.0125 seconds to the -1, and we want to find out what the half-life is for that. Okay? So the equation here is going to be T1 half is equal to 0.694 over K. Now, this label is important, and it's going to be important for putting this value in here with the label so you see what the answer is going to be. So we're just going to go ahead and plug that in there, 0.694 over 0.0125 seconds to the -1. Or you also see it written as 0.0125 over seconds. It means the same thing. I don't like that, it's a little clumsy. I like to put it there to emphasize the fact that we're going to be dealing with a flipping of this value when they divide. We're going to divide that out, and then the label for this is going to be seconds. And we can always change that to minutes or hours if it's a really large number, which is what scientists tend to do. They go to a time frame that makes more sense if you get like a really large answer. But we're going to leave it in seconds for this because it isn't that large. Anyway, so when you multiply, or divide that out rather, you should get an answer of 55.5 seconds. The seconds to the -1 becomes seconds to the +1 when it goes from the denominator to the numerator. So 55.5 seconds would be the half-life. Meaning for about every minute, you're going to lose half of your product and keep going until it basically becomes unavailable to be seen. Example, how long the previous question, using the answer to the previous question, how long will it take for the substance to have the following percentages remaining? Okay, so now this is where we use that, the 0.5 to the n power formula that I gave you for this. So we have 55.5 seconds as our half-life. But this is going to be the framework for it. So like, I'm gonna say that the number of half-lives, I'm going to make a column for that, and then I'm going to have the formula set up for this. And then I'm going to get my percent that I'm looking for here, and then I'll get my total time for my answer, what I'm looking for. So, in the first half-life, the formula setup is going to be 100% divided by 2 to the first power, and that's going to give us 50%. Now, since this is one half-life, then this is going to be 55.5 seconds times one half-life, which is 55.5 seconds. So half-life number 2 is going to be 100% divided by, now this 2 becomes the exponent of this 2 right here, 2 squared, that gives us 25%. So this is the second half-life, so this becomes 55.5 seconds times 2, which is 111 seconds. All right? Let's take half-life number 3. And that would be 100% divided by 2 to the third power. Divide that out in the calculator, or just take half of this. You get 12.5%. Since this is the third half-life, and this is 55.5 seconds times 3, which is 167 seconds. Our fourth half-life is 100%, divided by 2 to the fourth power. That is going to give us, when you type that on the calculator, or just take half of this, will give you 6.25%. This is the fourth half-life, so this is 55.5 seconds times 4 half-lives, and this gives you 222 seconds. And then the last one we're going to do is for the fifth half-life. This is 100% divided by 2 to the fifth half-life power. Divide that 2, or just divide that out in your calculator, you get 3.125%, which is technically 1/32, because that's 32. This is 55.5 seconds times 5, and we get 278 seconds. And that's how you do a halftime chart, a half-life chart, halftime. Halftime, you just analyze it and see who could have thrown the ball there, who should have caught that. No, wrong halftime. Half-life formula for this. So, practice problems. These 4 right here, it's on the second page of your script. And you're going to find 2 half-lives, and then you're going to find a succession of percentages for each one. So, looks complicated, but I think in the long run, it turns out not to be too bad. So, good luck.